Let's look at related rates in calculus, which is typically tied to geometry. Doesn't have to be, but it typically is. So let's talk about geometry as it used to be for you. And so one question you might get in geometry is to find the volume of a sphere with radius 8 feet cubed. I don't think we measure radius in cubic feet. Let's get rid of that. There we go. So a radius of 8 feet. And in geometry, that was pretty easy as long as you knew the formula for the volume of a sphere, which is 4/3 pi r cubed. And if you want the volume when the radius is 8, then the volume, and I'll even say volume at 8, would be 4/3 pi 8 cubed, and throw in your appropriate units. And that is geometry. And geometry was very nice because you just had a sphere and it was a sphere and nothing changed. However, in calculus, what we can do is we can actually look at a shape or a solid, that could be flat, could be two-dimensional, but we can look at it as the dimensions are changing because that is what calculus does. It allows you to measure things or look at things as they change. And so here we have a sphere. And this time the radius is increasing. So our sphere is blowing up. Think of it like an expanding balloon. But we have a radius that is increasing at 2 meters per second. And it wants you to find the volume, the rate, the volume changes at the instant the radius is 5. So we're blowing up this huge balloon. This is a massive balloon. And when the radius is 5, exactly how fast is that volume increasing? And this is where calculus helps us. And I always recommend if you are given a question or a sentence or a paragraph in math to try to get it out of sentences and into math language. So first thing I would do for this problem is I see that the radius is increasing at 2 meters per second. Okay? Anytime you see a reference to increasing or decreasing, you should be thinking derivatives. And so this is essentially saying the derivative of the radius is 2. So we could say r prime is equal to 2. However, if you look at the units, and you always want to pay close attention to units, my units are in meters over seconds, and I really don't like the r prime notation in this case. I like the Leibniz notation, which is like dy dx. So this would be the derivative of r. And because this is over time, I'm going to say the rate of change of r with respect to time. So dr dt is 2. The question, find the rate the volume increases. So we're trying to find the rate the volume increases. That means the derivative of the volume. So we could say v prime, but again, keeping with the same notation, we're trying to find dv dt at the instant the radius is 5. Now, when you are doing related rates problems, if they give you a unit of measure, so here they are giving you an explicit unit of measure. The radius is 5. That is not a change. That is a direct measurement of the radius. The radius is 5 meters. If you are ever given a dimension like that, ask yourself if that thing is changing or if the radius is always that measurement. In this case, it's changing. The radius is not always 5. So anything that changes, I put like a little flashbulb thing around it to remind myself that that's not a permanent measurement. It's just temporary. And the last thing you want to do is make note of what formula you're using. And in this case, we are doing the volume of a sphere, which is 4/3 pi r cubed. So now I have my volume, but I have to introduce derivatives to this. And so we will have to find the derivative of that whole equation with respect to time. Everything is measured with respect to time. It's meters per second. And so this turns into an implicit differentiation problem. We're doing the derivative with respect to t. So anything that is not a t has to get that implicit treatment that y would get when we were doing derivatives with respect to x. So the derivative of volume with respect to time would be just dv dt. On the right side, 4/3 and pi are constants. So I'm going to ignore the 4/3 pi, and then I will do the derivative of r cubed, which would be 3r squared. But again, r is not a t, so I have to give it the implicit treatment. I have to multiply by dr dt. So I started with the formula for volume. I differentiated it to introduce dv dt because that's what we're trying to find. And at this point, you plug in everything you know. So here we are looking for dv dt, so I will not plug anything in for dv dt. On the right side, I can plug in 5 for R. Now I can plug in 5, and I can plug in 2 for dRdt, and I am at the same time going to cancel these 3's. So we will end up with 4 pi 2 squared, 5 squared, R is 5, and dRdt is 2. And when you multiply that out, 25 times 4 is 100 times 2 is 200 pi. So dV dt is 200 pi. And then we have to put on units. And the easiest way for me to get units, there are other ways, but the easiest way for me to get units is simply to look at what we found. We found volume over time, a change in volume over a change in time. And volume would be measured in cubic units. So if my radius is measured in meters, my volume would be in meters cubed. And my unit of time is seconds. So there is a related rates problem, and there's your final answer. And always, always make sure you include the appropriate units for whatever it is that you found. Let's also get one more here. And this one we were talking about a rectangle. So the base of a rectangle increases at 2 centimeters per second. I'm going to stop there and make note. Base increases at 2 centimeters per second. So that means the derivative of the base with respect to time is 2 centimeters per second. Its area increases at 7 centimeters squared. So again, I'm going to take that out of a sentence, and I want to write that in math language. It's a lot easier to process if you get things out of sentences and into a math language. Centimeters squared per second. At what rate? Here's the question. At what rate is the height increasing? So we're trying to find dH dt. There's my question. When the base is 4 and the height is 5. So we're looking at a point in time when base is 4 centimeters and the height is 5 centimeters. And again, if you are ever given a direct measurement like that, you need to notice or make note of whether they are always those measurements or if they are changing. And in this case, both the base and the height are changing. So I put that in a little flashbulb thing. And that is to remind myself not to substitute those values in too early. We have to wait and plug those in after the derivative, not before. So we're dealing with a rectangle, the area of a rectangle, so we need to use the formula area equals base times height. And we will need to differentiate this with respect to time. We are measuring everything per second, so we're going to do the derivative with respect to time. Left side is really easy. The derivative of A is dA dt. On the right side, we have to remember that derivative rules still exist, and BH is a product. We have to do the product rule. So the derivative of B is dB dt. We will leave H alone, plus leave the B alone, times the derivative of H. And after you find the derivative, then you plug in what you know. Do not plug in the 4 and the 5 before the derivative. You plug it in after the derivative. I'm going to plug in everything we know. dA dt is 7, and I'm going to leave the units out. I don't plug in the units when I'm substituting my values. dB dt is 2. H is 5. I can plug in 5 now because I have already found the derivative. B is 4, and we are trying to solve for dH dt. And so that's going to be 7 minus 10 is negative 3 over 4 equals dB dt. And there is your answer. So I finished that up really quickly, but once you substitute the values, you can go back to Algebra 1 solving. I did forget units. I got to throw my units in here. So let me give myself a little bit of room to throw units. The derivative of the base with respect to time. The base, B, is a linear measure that would be measured in centimeters, linear measurement, and my dt would be measured in, we are doing seconds for this problem. So there is our answer. Always, always, always include your units. So there are two fairly straightforward related rates problems. They can get more complicated, but there we are.